Welcome to the lecture on robot mapping. I hope you had a nice vacation time and good holiday. Now we're back to school again. So I hope some of you still remember the least squares that we did before Christmas. The lecture today bridges these two concepts, SLAM, which is the problem we are addressing in this lecture, and least squares. And in practice, what we're trying to explain today is how you can apply least squares principles to solving the simultaneous localization and mapping problem. At the beginning, if you remember, we had this distinction of three different approaches for solving the mapping problem. We have seen at the beginning of the lecture the filtering approach, so the Kalman filter and the particle filter. And from now on, we're going to see what's inside this box, these graph-based approaches. And we can basically say the graph-based approach actually means that we are using something called least squares to the problem. We'll see the connection between least squares and graph-based today in the lecture, and from now on, we will see how we can different methods on using this graph-based approach for SLAM and different way of addressing the problem that arise on this formulation. So before going there, a bit of recap on least squares. So in general, and as we have seen also in the last lecture, least squares is an approach for computing a solution of an overdetermined system of equations. Okay? In general, this is a linear system that's and it's called linear least squares, but we also have seen how to do it for systems which are nonlinear. And the knowledge of overdetermined basically means that we have more equations than unknowns in our system of equations, and also means that there cannot be, so it might be that there is no unique solution, there is no solution, so we are going to find a solution for our unknowns that minimizes a certain error. And to define the error, we use a squared error, so therefore we go from an overdetermined system of equation to a least squares problem, which basically means instead of trying to find the solution of the equation as it is, we try to minimize the error from our equation. So normally you have A equal B, and instead of trying to find the exact, we try to find the minimum values of X and multiplied by A is close to B. And this is not just for SLAM, it's a standard approach for a large set of problems, and as we've seen also in the last lecture. And today we are trying to see how we can apply this approach to SLAM, and we'll see that this also results in a graphical structure of the problem. So here is our graph, as I promised before. So when we do graph-based SLAM, it's basically we are relying on a certain graph structure on poses of the robot, and sometimes you can also include landmarks that the robot observes over time. And we basically have these poses, it's where the robot was at certain point in time, and we connect then these poses with edges in this graph, and each of these edges is basically a measurement between these two poses. So when the robot moves in an unexplored environment, we go over time, and we connect each poses at time, let's say t, with the poses at time t+1, and the measurement between them is the odometry measurement. So it's what before in the filtering approach we were calling the motion model. No? So how the robot moves is connected by, let's say, described by this arrow here. And instead of doing the filtering in terms of, I know the robot is here and then I want to know what's the next position, we just consider these two as unknown in our system, and we know that there is a relation between these two, which is given by our motion model. Okay? And again, the measurements are uncertain, so we need to consider the uncertainty and the fact that there might be bias and so on. Okay? If the robot goes around and then at some point revisits parts of the environment, we have other kind of observations. These are observations or measurement between a robot pose at a certain time, let's say in this case t, with the poses that have been where the robot was a long time before. No? That is similar to what we've seen where we've done Kalman filter SLAM, for instance, when the robot was going around and then closing a big loop and coming back. And at that time, we were associating landmarks. And in this case, we're just associating poses. Okay? We'll see how to compute these associations later on in the class. But for now, you just assume that if you're looking at the same part of the environment, you can compute a virtual measurement that tells you how the two poses relate to each other. Okay? So the idea somehow is this. Imagine that you go with the robot around, so you do a certain loop, and at some point you arrive at this location here. And let's assume here you now observe this part of the environment, and from here you had observed, let's say, this other part of the environment. Okay? And now, if we know that these two are the same, we can compute the measurement indirectly between them. We can just take this measurement here, this measurement here. We can compute the displacement between these two. Okay, so in such a way that we try to align these two using ScanMatcher, for instance. And this gives us an indirect measurement between these two poses. Okay, because they are observing the same thing in the world. And that's what we put in this arrow here and this arrow here. Okay? So basically, this whole concept is to build a set of a graph with different with a set of nodes, and all of these are poses where the robot was during the time. And then we connect them by direct measurements from odometry or virtual measurements from our sensors. Okay? Once we have that, we can actually convert this graph into a least squares problem, and then we can solve for the poses of the robot, and we obtain the map of the environment. So the idea here is, to summarize, we have a graph that represents our problem, and as you've seen, this graph is made of nodes and edges. Each node corresponds to a pose of the robot during time. So we are basically embedding the trajectory of the robot that did in different time into space, and we then compute for each edge, so between two nodes, an edge is the measurement of the displacement between these. And this displacement can be a temporal displacement because the robot is moving over time and we have a motion model that tells us how the robot moves, or can be in some sense a spatial or a data association displacement that comes from the fact that two poses are observing the same thing in the world, but just at different time, and we can relate them by just considering what they are observing, aligning what they are observing, and from this alignment we get a measurement of the displacement between the two poses. Okay? Once we have that, we can build a graph, and that's where this graph-based SLAM keyword stems from. We find a node configuration that minimizes the measurement error. So basically, we have a lot of these nodes. We can move them around, and we try to find the configuration of them such that each of the measurements that we have here is minimized. So basically, each of these edge or each of these measurement is one equation in our least squares problem. The poses of the robot are our poses, and we have the measurement function that gives us the equation there. So in some way, we can say we know a least square is something like ax equal to b. This will be our system of equation. We transform it in something like minimize ax minus b squared. Now that's our least squares formulation. And now we encode the measurements into the a, and we'll see how we do it later on. The x are our robot poses. Okay. And the b's also comes from the measurements. So basically the measurements tells us this is the value of our measurement, okay, so what we obtain from our sensor. And the A is how the measurement relates to the state, which is what, for instance, we have seen as our measurement model. And you normally have something like, this is my measurement, this is equal to a function of the state, this is our observation function. And you normally then, a measurement is something that says, I can predict it from here, and then I have my real measurement from the sensor, and I try to minimize that. So that's what we are trying to do here. We have this part here that predicts the measurement value from the state space. This part here is the measurement that we obtain from our sensor directly, and we try to minimize the error of the measurements. How do we connect this to that? We'll see in the next slides. And we need to define a few blocks to get from the graph to there. Intuitively, how does this help for SLAM? So what we have is that, imagine this as an example. This will be the laser data collected with the robot in a certain environment, and in here we just project them using the odometry as the poses for the different laser measurements. Okay, and as you can see, this is not consistent. It's a bit of there's a lot of double walls. There's not a nice looking map. No, and we have seen before that with filtering we can get a better map, and now we'll see how we can do it with a graph-based approach. So the first thing that one does is we build a graph, okay? So by considering the way we explained it before, by considering the odometry information and data association information. Once we have the graph, we completely remove all the laser scan from our problem. We just rely on the node information and this virtual measurement that we computed between the poses. And we can abstract the problem just in terms of poses and measurements between poses. Once we correct that, we might get a better configuration so that the individual nodes which are here are put in a way that minimizes this, so minimizes the expected observation with respect to the real observation. And once we have that, we can then re-render a map of the environment by just taking mapping with known poses approach, for instance. We know where the different poses of the robots have been taken in the global frame of the environment. We consider them fixed. We get all the measurements, and we do mapping with known poses given the known poses from the optimization. Okay? Is everything clear so far? Any question? Okay. So, in practice, this is very abstract and very easy. I said we have a graph, we have some measurements on. But the whole approach is actually divided in two main steps. One part deals with the construction of the graph, and we call it in literature as a front end. We call it front end, and this deals with two main aspects, two main issues. One is to find out how to connect the different poses. So there is a data association part in here where you say these two nodes are observing the same part of the environment. So there is a decision problem that tells us are those two poses taken in the same part of the environment or not. And the second thing that it does is populating the measurement. So there is a topological nature that says I connect different poses, so that gives us a skeleton of the graph. And then there is a metric nature that tells us these two poses are connected by measurement of, 2 meters in front, and the uncertainty of this measurement is 4. No? So basically it gives us the connectivity and the relative measurement between poses. Once we have that, we get this graph, and we have what's called backend, which is a system that solves that. So basically it takes this graph, it builds a least squares problem, solves the least squares problems, and gives a solution to the SLAM problem per se. Okay? One can see them as two isolated entities. Of course, the backend needs a graph from the front end, But sometimes also the results of the graph optimization can be used by the front end to improve its results, because if you have something very close, you can use if you have something close to the optimal solution, you can use effective heuristics in the front end to make sure that the connection that you build are actually consistent, are good connections, their measurement is computed correctly, and so on. Okay? The topic of today is optimization, so we are going to go on the back end, and somehow the back end has been addressed more than the front end. Reason being, the back end is a nice abstraction, and you can use it for a different type of front ends, while the front end strongly depends on your sensor data. So it's hard to find the definitive front end for any type of robots, but you can find very good abstract backends that can be used in different scenarios. Okay? We'll see the front end construction, or how to build the front end, towards the end of the lecture. So after we've seen a couple of backends and how to deal with imperfect front ends. Okay? So what's the graph? As I said before, intuitively, this graph represents poses and measurements, but more formally, we can say it consists of n nodes, x, and we write it in this way. This is basically the variable x from time 1 to n, and for x, with x we indicate the pose of the robot. So according if you are in 2D or 3D, this is either a 2D transformation or a 3D transformation. And we will often use that or describe that in terms of homogeneous coordinate. I don't know if you remember the beginning of the class where we had a bit of review on homogeneous coordinate and projective geometry. But we'll see that if you describe that in this way, it's easier for a lot of computation that we need to do. So once we define that, it's clear. So basically we let the robot drive, and we can decide to get one snapshot, one poses every x seconds, or every time our odometry gives us a measurement, or we can just decide once the robot traveled 1 meter, I get one pose, and so on. So we can have a very easy strategy to decide when to consider one pose as one variable in our optimization problem, or as one node in the graph. A bit more tricky is to understand when we have a measurement or edge between these two nodes. And we basically have two kinds of measurements. The first kind of measurement is what's called an odometry measurement. So whenever the robot moves from time I to time I plus 1, we have an odometry measurement. So we have a connection that comes from our motion model, and we describe it xi plus 1, and there is an arrow there. Okay? So just on a side note, we often say that the motion model is something like this, that we have x at times I is equal to, let's write it in a linear way, it's equal to f x I minus 1 plus b u at time I. No? So that's how we can say it in a linear way, or if you want to do it in a nonlinear way, we say it's a function f of the previous state e minus 1 and the control u at times I. Okay? So that's the usual way we write a motion model. In the way we write it for a least squares problem, we can have a different way of writing it. One is, for instance, to say I just take that my measurement function will be something like xi minus f xi minus 1 ui, and then we will have that this is equal to 0, no? Because we need to write it in a way that is a function of the state and there is a measurement in there, no? Because we need to go to something which is ax equal b in some way, no? Or we can just, if you look at this in this way, you can just say that this part goes on the left, so we will have, but we need to divide this, if it's nonlinear, in a different way, but we can say that xi minus fxi plus 1 A minus 1 is equal to B ui, no? So we basically change the concept of motion. Instead of saying I'm in a state x and apply a motion, but just considering the robot was in state x at some point, is state x at I plus 1 at another point, and the difference between these two will be our motion, okay? If you look at it from a transformation point of view, it's probably an easier way to see it. Because what we have, let's do it down there. In terms of transformation, we have this. Originally, this is our reference frame. The robot, this will be the 0. There is a transformation of getting the robot at xi. Okay, so the robot moves around and at some point reaches this point. We have our motion model, which is another transformation that brings the robot to x I plus 1. Okay? Let's take the same one, minus I and I. No? And basically this is what we have from this function in some way. Now we have the I minus 1, and the I is this part of the transformation and this part of the transformation that goes there. Okay? Now, if we have this and this as variables, so these are the elements that we can change and we can find the solution from that, we can also imagine that we have another transformation that goes to xi, okay? And we can have as our measurement just this part here of the chain, which is the real measurement that we have, and this is this ui. And then we have this part, and we can compute a virtual, or we can compute an expected observation between these two variables by just taking this measurement, this transformation, and then to this transformation applying the inverse of this transformation. No? If we do that, it basically gives us the path from here to there. So if you look at this from a transformation point of view, you will have, I apply this, and then I apply the inverse of this, and I get the transformation between the two. No, that's how it works out. So we need to invert the concept we have of motion, that is something that moves the robot, with something that is an observed motion given where the robot is now and when the robot will be in the future, or where the robot was in the past. Okay? Any question on that? Okay. So this is one type of measurement we have. The second type of measurement comes from data association. And as I said before, it's this type of measurement that when the robot sees the same thing in the environment, he aligns them together, and we get a transformation between xi and xj. In here, we can imagine that the robot at xi has this observation from the sensor, so he sees a corner of the wall. The robot xj also sees the corner of the wall, but it's in a different location, so if we put them together, it will be somehow around here. When we do a scan matching, so we can actually align these two sensor data, and this creates a virtual measurement of the position of xj seen from xi. Okay? So if you look at this, this is again an observation of two relative poses. It's very similar to this kind of sketch here, no? Because we had xi minus 1 at some point, we had xi at another point in time, and now we have another measurement, but this time it comes from the scan matching. Okay? So the idea here is that if we consider both the motion model and a scan matching or an alignment between poses as the same kind of measurement, so as both of them as relative measurements between two poses where the robot was at some point in time, we actually do not need to do any distinction between the motion model, the observation model, and where this transformation comes from, but we can just have a unique framework where we say, I have relative transformation between nodes, and I know how to compute them from the different sensors I have in my robot, but once I have them, I just consider them as one entity, and everything is very neat and very nicely described by just one type of measurement. And this simplifies a lot in terms of coding, in terms of understanding the problem, and in terms of implementing and solving a SLAM problem. Okay? So, if we see this from a point of view of transformation in homogeneous coordinate, we have seen that using homogeneous coordinate, we can describe transformation as just a matrix that takes the transform a point by just doing matrix multiplication. So we have a point in homogeneous coordinate, we have a matrix that represents the transformation, and to know where the transform point is, we just take this matrix, we multiply the vector on the left side, so we have matrix, vector, and the result is the transformed vector. So since each of these frame, each of these robot poses can be seen as a transformation from the origin, we can just consider all of them as transformation. And if you look now at the odometry-based edge, we have that the transformation between these two poses is actually the pose times I inverted, so -1, multiply the transformation of the poses at I plus 1. Okay? So basically means I take this, I invert it, so I go there, and then I apply this transformation, and I get a prediction on this measurement here. Okay? So if you look at a scheme like this, it's pretty easy to see. So I am somewhere here in the world. I have these other points, and I want to know how do I go from here to there. Okay? And for going from here to there, you can either use the direct path, which is this one, and this is given by the direct measurement I have from my sensor, or I can use the second path that goes to the origin. Okay? And for doing this, I have originally this vector here, or this transformation. I can invert it, so I go back here. So from here, I go down here. I use the direct one, I go here. And again, I have the same path there, but from a different point of view. Okay? And that's basically what this is telling you. It's telling you, I predict my measurement by going backwards from the previous pose and forward with the new pose. And this should be as close as possible as what my odometry is telling me. The same is for the observation-based edge. I have a matching system that tells me these two poses are related by this transformation, which is the same thing here. And then I go back from the first pose, and I go forward from the second pose, which is exactly what happens here. The difference is that an odometry measurement always relates two poses close in time, and a data association measurement or an observation-based measurement, or edge, as you want to call it, relates poses which can be very far away in time. Okay? So the only difference is on these indexes and how they can be. Okay? Any question on that? Okay. So, getting a bit back on refreshing on homogeneous coordinates, the interesting and important thing for what you need to care about is that homogeneous coordinates are a tool used in projective geometry, and it's just a way of describing transformation and points in a very elegant mathematical way. So there is a lot more into projective geometry that we are not caring for now, because we always care, we don't care about projection. We don't have a sensor that projects points into another plane. So for instance, we are not using cameras for now. We are using a full observable 3D or 2D environments, but we exploit the properties of simplification of the transformation, which is that using a single matrix, we can represent a lot of affine transformations. We can represent translation, we can represent rotation, and in principle, we can also represent shear and scaling and so on. But for what we are concerned right now in terms of relative measurements, we can say that we can use, with a single matrix, we can express at the same time rotation and translations. We don't have two different components, but we just have one single mathematical tool. It's matrix multiplication. And with that, we can describe everything that can happen when we move a rigid body into space. Okay, so that's the important thing for you right now. This means, imagine we are now in 3D. We are just extending the world with another dimension. And if we are not doing any projection, we always will have a 1 into the last dimension. In this case, you go from 3D to 4D vectors. We can always go backwards. Whenever we have a W here, we can just take the first component and divide it by W. For you that maybe know a bit of projective geometry and camera, this is related to the focal length that you have. But for our case, this will always be 1. So, which means that whenever we want to get back the x, y, z from the point, we can just take the first 3 elements, because dividing them by 1, it's basically the same as saying we take the elements. But the important thing is the transformation. So if you want to have a translation, we can just take a matrix that is made like this. It's basically an identity matrix with the different translation on the x, y, and z as column on the last part. We can do a rotation similarly. We have 1 down there, 2 zeros, and the rotation matrix. And if you want to do translation and rotation together, we basically have to just plug here the translation vector. Okay? And this allows us to simplify everything just considering matrix multiplication. So another thing which is also important is the noise in the measurement. So far, considering the transformation, we just consider the value of the measurement itself. So the value of the predicted measurement and the value of the observed measurement. But we didn't say anything about noise. So those transformations, those measurements are always affected by noise. And in this case, when we look at information, when we look at graph-based SLAM, and when we look at least squares approach, we consider the information matrix, and the reason will be clear soon enough. And with this information matrix, we encode the uncertainty of each edge. Okay. Now, ideally, the bigger is the information matrix, the more certain the more certain this measurement is, and also the more we want to trust this measurement. In terms of optimization and least squares, this basically means that each of these individual equations that we have in the least squares will be given a different weight. Okay, and the stronger is the weight, the more the mismatch between the prediction and the observation will influence the minimum. Okay, so if we take now 2 measurements and one of them is multiplied by 1,000 and one is multiplied by 1, of course we'll try to make sure that the one that multiplies by 1,000 is closer than the one that multiplies by 1. Okay, and that's how the noise and that's how the uncertainty comes into play into a least square problem. Okay, now few questions to you. What do you think in general will happen if we have scan matching or if you have odometry with respect to the information matrix? How can they relate to each other? Any idea? Will one be bigger than the other in general? Yes, no. Imagine that you're using a very precise sensor, like let's say a laser scanner. No? Very precise laser scanner, and we have an odometry which is not as good as the laser scanner. What will be the relation between the two? Which one will be in generally bigger? Who votes for having the scan matcher bigger? Raise hands. 1, 2. Who votes for having the odometry bigger? Only 1. Okay. Yeah, so in general, we can say that the more precise sensor will have a bigger information matrix. So if we use a laser scanner versus an unprecise encoder, we'll probably have the scan matching information matrix way bigger than the odometry information matrix. But what's the important thing here is that the odometry information matrix do not strongly depend on the environment. And the reason is that those are proprioceptive sensors, so they're just looking at what the robot is telling them. And basically they don't care about how the environment looks like, so they will be roughly the same regardless of how much structure is in the word. The scan matching, on the other hand, strongly depends on the structure in the word. So if the robot doesn't observe anything, it's in outer space without looking at anything else, he has no idea what it is, so it will be a very small information that he can get. And the interesting thing is what happens when we are in some particular cases where few directions are not observable. And that's the case if, for instance, we only see a pole or if we only see a featureless corridor. Because what will happen is that, imagine you are in a corridor like this, the robot is here, one pose is here, and another pose is here. And none of them can see the end or the beginning of this corridor. When we try to align those two poses, we will have a very certain direction here. So we know a lot that this can only be in this location because we can align this and this wall, but we have no idea on where, on this direction, the two poses align with each other. Okay? In mathematical terms, this means if you look at the information, the covariance matrix, there will be an infinite covariance, as we've seen before. So it's really uncertain where the robot can be. In terms of information matrix, this is zero information. So I cannot tell you anything about that. And these are related by the fact that the information matrix is the inverse of the covariance matrix. So if you just take one direction, 1 over 0 is infinity or so. Okay? The interesting thing is that this is not the case for the odometry. Okay? So while in general the scan matching or the sensor-based measurements are more important than the odometry measurement for resolving the problem, that's not the case where part of this environment is not observable. Okay? So that's why we need both of them in some way. The same is if, for instance, we just observe a pole here. No? So there is no way of knowing exactly where they are, but we just know that they can be anywhere in a certain circle with a certain radius. No? So we have, again, in this case, we might have 2 degrees of freedom fixed. One is the orientation, one is the y. In this case, we only have 1 degree of freedom fixed, which is a function of the y and z. No, we can only be on this circle. Okay, is it all clear? But only on this direction.
Yes, but in this direction, the pulses get scattered. But in your odometry model, it's like maybe a banana-shaped, small scatters and scan matching, right?
Not really. So what might happen is that if you have few features, like imagine you see some dents, then right, because this part of the wall and this part of the wall might help you in aligning in this direction. But otherwise, you have no idea where you can be in this direction. So you can, I don't know how you can, how I can, if there is something that I can explain better. But the concept is, imagine you are, imagine if you are in a maze, no? In very clear maze, and you only see your right wall and your left wall, and you don't see anything else, no? And now I put you at the beginning of this corridor, and then I put you at the end of this corridor, but I just blindfolded you, and I move you around without you moving. You can say that you are roughly where you were before in left and right, but you cannot say anything about how far you walked, because you didn't measure any distance, no? And that's basically what this means. It means that if you want to scatter it, the odometry might have, let's imagine in covariance matrix, ellipses. The odometry will have something maybe very big, or let's say, let's do the banana shaped. So it went forward, it's a bit, so it might be something like this. I'm just now assuming, okay? And it's very large in this direction, and also in this direction, but and this will be our corridor. The scan matcher will do something like this. It's very precise in this direction, okay? But then it will be kind of infinite on this line and infinite on this line if you just want to draw an ellipse there. So you cannot draw it because it's infinite, so it's kind of a singular case. But that's what will happen. And if we do it, if you consider then the information, it basically means inverting this, which means we have a 0 in there. So even if this is kind of more uncertain in all direction, the other one is actually completely uncertain in one. So that's what it means that it's singular. It's not observing one dimension. Okay? Any further question? Okay. So how do we again write down in a bit more formal way? We have these two poses. We're now analyzing one edge at a time. And we can try to expand the edge in terms of imagine that there is another variable there. And this variable is the measurement that we have. And this variable has an expected value, so it's z, which is the measured value, and an information, which is our omega there. And we can consider these two nodes, xi and xj. And we have something that we call error, okay? And the error, if you consider a very simple linear case, it's basically the prediction minus the observation. But in general, this can be any complex nonlinear function according to what is the problem that we have at hand. What is the, if it's a 3D in 2D, if you want to add also external point, and so on. But we'll see which is the function that we use later on. And the goal is that to find the configuration of x, so the optimal x, where each x is a pose of the robot, that minimizes this here. Okay? If you recall from least squares, what we have here is actually a weighted least square problem. We have the error transpose the error. Imagine this is an identity matrix, which is exactly the norm of the error. Now I delete it from the whiteboard, but it will be the least squares of the error. And now we're putting a information matrix there to weight the different errors in according to how informative they are. And we sum all them up in there, okay? If we now expand everything, we have that each ij where we have a measurement. So if you now look at how this can go into a least squares problem, again we can say these are subset of our state space, xi and xj. We can write the error ij whenever we have an edge between node I and node j. And this is all the individual thing. But we can also write them with respect to the full state space. No? The way to extend this in this way basically means that k is the set of measurements that we have. And then this function ekx, it's like extracting the parts of the state space that are needed for this measurement and then calling ej on top. No? So we just now try to abstract everything. And because we want to get something which is a function of x of our full variable set. But now, what is our state vector? We know already that our state vector is composed by the set of all the poses over time of the robot. So we have that our state is a vector composed by stacking all the individual poses over time, one after each other. And one block is according to if you are in 2D or 3D, this is x, y, and theta, or x, y, z, and the triangles. Or this also depends on how we want to represent the orientation, but in principle, we have for each xi a way of representing the parametrization of this specific pose of the robot in the world. Okay? Now, the only thing that is left to explain and describe is the error function. Okay? So, when we are this abstraction with respect to relative measurements, we can express everything with respect to relative measurements by saying I have xi and xj are my transformation of the individual poses described as a matrix, as a transformation matrix. My function now is the inverse of this, of one transformation, the multiplied direct transformation. Z, again, we can take the this transformation here, we can express this as transformation matrix, and we then invert it because we want to go, one goes from here to there, and then we want to go backwards, that's why we invert it. And basically the idea is that whenever we do a full loop around this by using the poses that we have in global frame, the relative transformation, we basically end up in the same place. And this should be the identity transformation. And then we get it back with respect to this function, which is transformation to vector. It just tells us it takes a transformation matrix and gets back the vector representation, which basically means if we have zero translation, we will have a zero in the vector, and if we have an identity as a rotation matrix, they will end up in a zero angle for the angle part. No? So it's just a way of writing, of going from a transformation in terms of matrix and a transformation in terms of vector representation. Okay? So whenever we have the error as a function of the all-state vector, we can include, since we know that x is stacked, this xi and xj are just a subblock of the state vector that corresponds to each individual poses. And the error takes 0 whenever the so the measurement from the sensor is exactly equal to the path from this pose to the next one. Okay, so basically what will happen is that if they are exactly the same, this will end up as an identity matrix, and whenever we put the identity matrix into this function, transform the transformation to vector, this will end up with 0 translation and 0 rotation. So at the end is a 0 measurement. It's 0 error. Okay, is it clear? Okay, so now that we have everything defined, we can see how we can solve this least squares problem in terms of the Gauss-Newton algorithm. So the one that we described also in the last lecture. So the idea here is that we have our error function, which is a nonlinear error function, and we just go through the definition of the Gauss-Newton algorithm, which is we first linearize the error function. Once the error function is linearized, we have a linear least squares problem. And once we have the derivative of this, we can put the derivative to 0. We get our h and our b, if you remember from the last lectures, which basically means we have now our nice linear system. And we solve the linear system, and then we iterate to the new solution. And we go on until we converge to a minimum of our problem. So going step by step, we again can write our linearized error function in terms of the current initial guess, the current guess that we have, plus the displacement from the guess. And this can be approximated via Taylor expansion by the first order. So we have the function evaluated at the previous initial guess, plus the Jacobian of the function times the displacement that we are considering, times the delta. And j is again the Jacobian, so the derivative of the function with respect to x. That's an interesting question. So what is the structure of this derivative? As we have seen here, we have x, which is the whole state space. Delta x is on all the state space. And now we have the j, which is something that is a derivative of this error function with respect to the whole state space. How does this error term depends on the individual part? So does it depend on the all the state space or just a part of it? Any idea who's voting for it depends on just a part of it? Okay, so it is only depending on x, y, and xj. As you have seen, is all relative transformation. This basically means that the Jacobian has a particular structure, okay? And the structure of the Jacobian is that it will be zeros almost everywhere, besides the part that are that depends on the variables which we are considering. Okay, so in case we have I and j, it's zero everywhere besides the block ij and the block I and the block j. Okay, so this also implies that it is very sparse, and given this sparsity, when we need to then compute the b's and the h by summing everything up, we will see that the structure of the Jacobians makes a sparse structure also on the Hessian, so our H matrix. And this structure actually reflects the adjacency matrix of the graph. Okay? So if you now look at this, we have, imagine for one measurement that only involves I and j, and this will be I and this will be j. We have that the b's are when we multiply this by the information matrix of the edge and the error, we get that again we have a sparse B for ij, and the same things applies for the h. No? We get our Jacobian here, which is sparse, we get the information matrix, we get the other Jacobian here. We end up in a matrix which is very sparse, and it's non-zero only in the 4 blocks that belongs to the II block, JJ block, and the mixed IJ blocks. Okay? Now, if we sum everything up all together, we end up in a dense B, because we will have a lot of different sparse vector, but eventually we will use all the variables in the state space, because in the worst case where we have no data association, we always have an odometry chain, so each node will be part of one measurement from the odometry, from the motion model, and we end up in a dense B. But the same does not apply for the H. And what will end up is that we will have a very sparse structure, and the interesting thing of this structure is that every off-diagonal non-zero element corresponds to one edge in the graph. Okay? And that's the relation which is there between the graph-based, the concept of graph-based SLAM and least squares, and that's the structure, the adjacency matrix of the graph actually has the same sparsity structure as the Hessian matrix of your least square problem. Okay, so the sparser the graph, the sparser the matrix, and vice versa. So there is a connection between these two aspects, between these two mathematical objects. Okay. So, what is the consequence of this sparsity? Is that that when we get to the solution of this problem, so we end up that when we sum everything up, we only have few parts of this which are non-zeros for the coefficient, for each of the individual coefficient. And similarly for the matrix, so here is just opening up the whole real values that you put there. So we have these parts which are the ones that we compute for each individual edge. But the important thing is that solving this system is actually very quick, because we have that for sparse system we don't need to invert the matrix for solving the full system, but we can exploit few decomposition which runs in linear time, like a sparse Cholesky decomposition, or we can also use other methods like conjugate gradient to solve the linear system. So basically what happens is that we have a complexity that goes from being quadratic in the size of the problem to something which is linear or a bit worse than linear with sparse problems. Okay? And this is how our, again, linear system looks like. We have all the increment which we put into a vector, and these are our variables in the linear system. We have our coefficient vector b's, which is composed by the stacked element of each individual measurement, and we have our system matrix, which is composed by the individual blocks of the system matrix. Now here I'm just putting everything as an H, but a lot of these small block H will be zeros. Once we have this, we know that we can take the A and B's as the derivative of each error function for each of the edges. So basically what we need to do is we need to compute these Jacobian blocks. Once we have these Jacobian blocks, we can update the coefficient vector. So the idea here is that we can iteratively going through all the measurements that we have in our graph, and we just update the individual components, so the B's and the H for each measurement. We take the measurement, we compute the gradients, we update the B's by getting the E times the information matrix times the A, and the same thing is for the Bj, so we update the different elements there. We also update the system matrix by considering the 4 blocks, the II, the Ij and Ji, and the Jj blocks. And for the II, we just take A transpose information matrix A. Similarly for the Jj, where we just take the B transpose information matrix B, so the different derivative. And the mixed product, actually, you can also just compute one of them, because the other one is exactly a transpose of that. And that comes from the fact that the information matrix is symmetric. So you can just either take this one or the other one. It's your choice which one you want to compute, and just symmetrically put the other one there. And if you just iterate all over the measurements, you will end up in the full system by just taking the B's and the H at the end of the loop of the measurements. So the algorithm is very easy if you do step by step. The idea is, until you converged, you first build the linear system, which basically means taking the current estimate of the state space. You take the measurements that you have, and you end up in computing the H and the B's. Once you have the H and B's, you can use any sparse linear system, sparse solver for a linear system, and you solve the system, which is H delta X equal minus B, or if you want to put it in a least square, you say this is already the solution for the least square problem, and according to which solver you use, you will decompose H using Cholesky or using Kronecker gradient. But this is just a call of the sparse solver. And once you have the new deltas, you just apply the new deltas to the previous estimate, and you iterate over. Okay? Let's go on a quick example in 1D and the linear case. So imagine now we have just 2 poses. They're all linear, so it's in 1 dimension. They can only be on the left or on the right. And we have, as a measurement between xi and x1 and x2, just 1. So basically, those 2 measurements are 1 meters apart. We know as initial guess that both of them will be in 0, 0. So we don't know anything, we just put them at 0, 0. We have our only measurement is between 1 and 2, is 1 meter. Our information matrix is 2. We now go for our measurement function. We have, before we had z minus at the -1 times x at -1 and so on, but we can go from the matrix transformation to the linear by just considering that the inverse is the minus. So we'll have a minus here and we'll have a minus here, and whenever you multiply, it's like the plus in there. So if we take the Jacobian of this error function, we get that the Jacobian is 1 and -1. We now build up our system, so we have only 1 measurement, so we can only compute once. And we have that by multiplying E, omega, and J, we get 2 and -2. This comes from the fact that omega is 2. This is our J. Multiplied by 2, you get 2 and -2. E observed is 1, is the 1. We can get from here our error. So we get 1 times 2 times the vector, is 2 minus 2. Again, if you take these two vectors, it's 1 minus 1, you multiply by 2, you end up with a matrix that has this form. Okay? And now I want to try to solve for delta x. So we just say, I can just invert h and multiply by b. So it's the easiest way to solve this linear system. But we have a problem in this case. We have the determinant of h is actually equal to 0. No? So this means that h is not invertible, which also means that it's impossible to get a solution for delta x in this case. Okay. This is easily seen, but because for the 2 by 2 matrix, the determinant is the product of these 2 minus the product of the other 2. No, so we will have 4 minus 4, which is equal to 0. I will make a short break, like 5 minutes break. In the meantime, you can try to figure it out. What's the meaning of having the determinant equal to 0? Why is the case, and why one can, what can one do to address this problem? So, any idea why the determinant is 0 and why we cannot get any solution for the delta, given this case? Anyone wants to give it a try? So let's try to find out what we are trying to ask the optimization problem. No? So we are trying to ask what's the location of x1 and x2 with respect to the global reference frame, with respect to the absolute position in the world of x1 and x2. And the only thing that we are telling the system, the algorithm, is those two nodes are 1 meter apart. Okay? So as you can imagine, those two can be 1 meter apart. So imagine that they are here. No? One node is one tip of the presenter. The other pose is the other tip of the presenter. And let's just imagine this is 1 meter distance. If they are 1 meter away, if I am in 3D world, they can be everywhere in here, but they're still 1 meter away. If I am in just 1D world, they can be everywhere on this line, okay? And they will still be 1 meter away. So the reason of having this determinant equal to 0, it's basically meaning that I have not enough information for solving this problem, okay? So if you now consider, let's try to do an analysis in this way. Whenever I have a linear system in the way which is ax equal b, the rank of A, which tells us how many independent equations are there, tells us a lot about this system. Okay, so when the determinant of A is equal to 0, this implies that the rank is also equal to 0. Okay, so it's not equal to 0, but the rank is less equal than, let's say, n, where n is the dimension of the matrix. Okay, so basically it means that we have less equations that are knowns. So that's the meaning of having a determinant equal to 0. But we are trying to use a least square. We are trying to get something which is more equations that are unknown. And this basically means that there is always one equation less in the problem. And this is not because we don't have enough observations, we don't have enough measurements. It's because the nature of the measurements that we have. We only have relative measurements, not only in this case, but in the generic pose graph or graph-based LEM. We always thought about measurements between nodes, so relation between pairwise nodes. But we don't have any global measurement that tells us this specific pose is at this specific location. Okay? So whenever we have relative, everything can be very nice displaced, maybe perfectly displaced in a way that all the measurements are 0, all the errors are 0, but I can still move this rigid body around into space in whatever position I have, and I still have the same solution to the problem. Okay? So the only way to get a full rank matrix, so when we have the determinant different than 0, is actually adding additional measurements or adding some information that tells us where the where the pose will be. There are several ways of doing it. So one way is that we add something else. So we just add something on our edge. So we just put something like this. That could be 1, 0, 0, 0. This basically means that we are adding another measurement that that tells us one pose. So the first pose is at location 0, and I'm certain that this is at location 0. Okay, this is one way of doing it. You can put any number here, and actually will not change at all the results. Because this is just saying I'm now having a full rank matrix, and I'm telling you that I know where the first location is, and I'm telling you now with the B if it's a 0 or if it's a 1, if it's every position in the world that you want to put. Okay, this actually gives us an additional measurement in our thing that says this one. Let's say it's something I know for sure. And I'm telling to the problem that I know it by just considering as another measurement. Okay, so a measurement then will add something to the H, and in principle should add something to the B as well, but if you say that the initial location is 0, then it will just add a 0 to the B. And you can see this also as a prior, as we said before, on the information. So we can just say that I have a certain distribution over the initial pose, that it's my prior, and I can just add it to my whole problem in terms of individual measurement on x0. The most common used prior is just to fix the initial location to 0. So basically it's just, or to any values. In this case it's an x0, and most commonly is a location in 0, so this will be an identity matrix. And this is the way we express it in the least squares problem. We have an additional error function, which is a one-dimensional, or like we only consider one block of the state space, which is the block at 0, and only consider the transformation of x0. Okay? In this way, we have the full system ready, and we don't have this determinant of the Hessian to be 0, this rank problem. Okay? Another way of addressing it is if you have sensor that are actually able to measure the global pose of the robot at different point in time. No? One sensor can be, for instance, a GPS measurement if you're outdoor on your robot. GPS is able to measure the location of the location of something globally on the Earth. So you have one reference frame. It's able to just measure one single thing. And what you will end up is that you will have, instead of just one fictitious measurement on only one part of the variable, you will have a set of measurements that always have just one part of our graph, and will be like x1, maybe x10, x20, and the values here will come from the GPS measurement. So you will have something which is similar to that, and will just tell you that E of x, let's say j, from the GPS will be the usual transformation to vector of the zj minus 1, and this comes from the GPS, times xj, that comes from our current estimate, so that's the variable we are trying to estimate. So, and this is different than what we have seen before for the relative measurement, because we don't have here the xj minus 1 xi as before, but we have a direct measurement of one of the x's. Okay? If we have this kind of observation, if we have at least one of them, then we have a full rank system after that. Okay? And but that's not always the case. So if we have absolute measurements from an external sensor that gives us absolute or global coordinate, global estimate of a single individual pose, then we don't need to add the prior in our problem. Otherwise, we need to put at least one node to a certain set values, and normally we consider zero. We consider the first node to be in a 0, 0, 0, so the origin of the word in most of the cases. Okay, because at the end, what's important is building a consistent map, and then we can say, this is of my origin, and external someone can just say, okay, this origin is now this value, and everything is magically fixed in the new world. Okay, so I will show you now a real-world example of using a graph-based SLAM approach. Here you will see the full spectrum, so front end and back end at the same time. Is using a laser scanner. Here in blues you see the graph built so far. So basically there are a lot of nodes and edges between those nodes in there. You can see slightly here in black the map built. So like we do a rendering using mapping with known poses on the fly. There are a few things to see, interesting. So you can see now the robot is moving around and is observing part of this, part of the environment. At the beginning, it's just collecting measurement from the odometry, so there will just be a chain of this pose. The graph will just be one after each other. But at some point, it will, like soon, it will come back to this part, and you can see that here in red, you can see that the robot is reobserving part of the environment, so it's trying to get some of these poses together. It's trying to analyze if there are some connections. And right now, what happened is that he built the different connections, he did the optimization, and he ended up in a graph which is better optimized. The same you can see here, all these edges are the relative measurements between poses at a different point in time, but they're observing the same part of the environment, and so on and so forth. So it will just now again go around, build this connection, and build a consistent map of the campus. This is again the campus we are staying in, and I think we are somewhere in here, I guess. So now you have seen everything with respect to the global reference frame, but once we can also compute an estimate of all the different poses by considering one pose as given, okay, or with respect to one individual pose. This basically means that if you assume that certain variables are known a priori before the optimization, so we know that at a certain point in time the robot was exactly at this location, or we want to know how the other location of the robot are with respect to a specific one. So we can just say we keep those fixed and we optimize the others. How can we do it? So if we say that one variable is not optimized, we should actually have it disappearing from the linear system. And for disappearing it, what basically we do is we just eliminate the rows and the columns of once you have the full system, we remove the rows and the columns in the H matrix with these variables that we don't want to consider, and the same things, we remove the elements into the B vector that we don't want to consider for that. And the question is, can we actually do it? So what is the implication on the system and on the SLAM problem when we do this? The implication is, if you go back to the Gaussian case that we've seen before, we are now in a situation like this. So basically, there is a connection between least squares and maximum likelihood, as we've seen also in the last lecture. And basically what we are saying is inherently our distribution of the robot poses is a Gaussian distribution, which is modeled using the not the moment formulation, but the natural formulation. So we have the information vector and the information matrix. By cutting out part of the information vector, which is the B's that we are now considering in the least square formulation, and part of the information matrix, which is the Hessian that we are having in our least squares formulation, what we are saying is that we are conditioning on subset of the variables. So basically we are trying to find the maximum likelihood configuration of the remaining poses, given that we know some of them are fixed. Okay, so that's what we are trying to do. This is useful for several things. One usage is that instead of having a fictitious prior on one pose, we can also solve this gauge freedom of we don't know where these variables are in the world, but just saying I just want to have one fixed and solve for the other one. Or we can also use it for computing, for knowing how far in statistical term is a certain pose with respect to the current pose of the robot. Okay, so this is important because if we can determine the relative uncertainty between two poses, xi and xj, we can use it for data association. Okay, and for doing it, what we do is we compute the full matrix H, so we compute the full Hessian. We suppress the rows and the columns of xi. So basically, we are saying we fix xi, and this xi is the center of the world. I know the values of xi. And then we just compute the block jj, so the block of the other variable we are interested in, from the inverse of H. We can do it by inverting H and just taking the block, or we can also do it by solving a pseudo-linear system where we just want to extract the jj element of the matrix. I'm not telling you how to do it, but just keep in mind that there is a way of getting it quite fast. So we don't really need to invert the H matrix for getting that. Once we have that, this block will actually have the covariance matrix of the node xj with respect to xi. Okay, and we can use this covariance matrix for data association, because whenever we know that the two poses are too far away in terms of statistical terms, we can exclude them for the scan matching to find the virtual measurement. But if they are very close by, then we want to include them for the search for potential matchings from the front end. Okay? And this is an example idea on how it works out. So this is a graph taken from one famous data set, is the Intel data set. The robot is here. And what we did here, we just took the, we built the full linear system, we built the H matrix, we removed the rows and columns of this location of the robot being here, we inverted it and we just took the block covariance of all the poses on the diagonal, okay? And here this ellipsis will tell you how uncertain is the location of one pose with respect to the one of the robot being here. And as you can see, it happens what we expect, that very close to the robot there will be a low uncertainty, but the further away you go from the robot along the graph, the more uncertain the position will be. And especially the most uncertain one are the ones which are topologically far away. So there will be the part on this side of the map. And what you can also say is that if the robot is here, here you can see the 95% ellipsis. So I think these are the 2 sigma ones, so it's not 95, it's 94 something. And basically this means that all these poses here, they might be useful for data association, where the robot is searching for these measurement-based, observation-based constraint measurement between the poses that comes from aligning the scans. But we don't need to do any scan matching with all the remaining there because they are statistically too far away. So we can just eliminate them from data association search. Okay? Any question on that? Okay. So to conclude the lecture today, we have seen how to build a backend for solving SLAM, and we show that one way of solving SLAM in terms of the graph-based SLAM is basically applying the Gauss-Newton algorithm to a least square formulation of the problem. And for getting the least squares formulation of the problem, we can just consider the individual measurement that the robot can accumulate over time from the odometry and from aligning the scans or aligning scans between different poses in time. This all ends up in relative transformation between poses, and once we have all these relative transformations, we can go through all of them, build up a linear system using Gauss-Newton to solve the linear system, the linear part of the system, and then iterate all over again. So from the graph to the system, linearization, solving the linear system, again iterate. This is the state-of-the-art solution used in literature, academia, and also for in some commercially available products. The trick and the interesting property is that the H matrix is typically sparse, and this allows us to have a very efficient solution for the least squares problem. And one thing we didn't show is how to build up this graph, and this will come later on with, within the next lectures. And you can use a lot of available tools for solving the linear system. So in principle, you don't need to re-implement the solution for the linear system, but you have tools in MATLAB or in C++, whichever language or framework you want to do for implementing a SLAM solution. If you want to have a bit more details on how to build, how to solve how to formalize SLAM as a graph-based and the least squares problem, and how to then find the linear system and solving it, there is a tutorial, which you have also a link on the webpage of the class. It's a tutorial on graph-based SLAM, and you can just download it and you get more details on that. Unfortunately, there is no, the chapter in the book in the probabilistic robotics is very brief and doesn't tell you a lot about graph-based SLAM solution. That would be it for today's lecture. Is there any question? Anything that was not clear? Not well explained? No?
Sorry, I have a question regarding page 55 and 56.
Okay. Yep, 55.
For this, yes, could you please explain again about the certain uncertainty and how to calculate the relative uncertainty?
Okay, so the idea, probably then the whiteboard will be useful in this case. So the idea here is we want to not only get a notion on where the robot was at a certain time, but also an estimate on how certain we are in telling you the robot was there at that point in time. Okay? So basically it means if you get again our nice graph, let's do something like this, very simple. I want to know the position in the word frame, but we also want to have an idea of the uncertainty. Okay? Maybe something like the nice ellipsis of where the how uncertain we are with respect to this estimate. Now, H we have seen in the previous lecture on least squares is that whenever we have our H, that we can write it as J transpose omega J. Okay, this one is the information matrix of the full system. Okay, so basically what we have is a relation between the graph, the least squares, and a Gaussian multivariate random variable. Okay, so we will have that the solution of this, so our x, is equivalent to the mu, the mean of the covariance matrix, and our H is the covariance our H is the information matrix of that. Okay, so we can say that x goes with respect, so the state, the belief over the state goes with respect to a like a normal distribution, which has a mean that comes from the optimization. So that's the result of the optimization algorithm. And then we have H minus 1, which is the inverse of the Hessian matrix at the solution. Okay, because we need to compute the Jacobian, so we need to have a values for computing these Jacobians and so on. Okay, so that's how our distribution looks like. And this gives us a value for the mean, which we get here, and the value from the uncertainty. So that's what this guy is telling you. So you have a full dense covariance matrix when invert H, but if you want to know the, let's say, the absolute uncertainty of a pose, you can just take the block covariance, no? Because the absolute will be the marginalized. We are marginalizing a multivariate normal distribution. It means we're just taking the block that we're interested in. And in this case will be the diagonal block. Okay? Now this doesn't tell you anything about how those are related with each other. No? So to get the relation between each others, we should take all the different blocks that we want to have. There's another way of getting it by not inverting this, and this is what I mean by the relative uncertainty. So what you can say is like, I now fix one of them, and I do the same, so I just take the condition distribution. So instead of taking just x, I try to take x given xi, no? And this x is actually everything minus I, no? So I condition the full state space with part of the state space. And that's, I think, something here. Now, so that's the idea here. We have everything up there, just the part down there. And we actually on this side, we have everything up here and the part down there. And instead of now having the covariance matrix, I have the information. So it's roughly, we can do, forget about this, but we can do just that. No, we're all interested in the information there. Okay? So once we have the information, we can just eliminate part of this, which means I'm fixing now that. And again, this goes as a normal, which will have this, the mu, and this one given xi at minus 1. This basically means that I'm eliminating the rows and columns that I don't care. This is the solution of the system when I eliminate everything that doesn't care. No? By having this, again, forgetting the relative now uncertainty, I can just take the blocks, because this is given, and I want to just know the uncertainty of this variable, given that. Okay, so that's the idea. The reason why we do in this way and not by just inverting everything is that inverting everything is expensive, but when we do this in this way, getting the blocks are actually not too expensive. Okay? You can, let's see, how can I do, let me think. Yeah, you can write the system in a way that you just get the blocks. Okay? So, I don't recall it exactly, but So there is a way of getting few elements out of the inverse of H by just solving an optimization, minimization problem, like a linear system equation, not an optimization problem. So you can get just few elements in very quick way. Okay? That's why one cares about this. Otherwise, it's equivalent if you consider the two approaches if you want to have the relative uncertainty between variables. It's just more efficient in this way. Okay? Any further question? No? Okay, so that's it for today. See you next week.